course. Well, we're going to get going. Obviously, last week, and we got a couple of topics we want to go over tonight. Air management is kind of the overall title here in this first section, talking about air in the system, the importance of it, and how it can be a problem as well if not handled properly. Then we'll get into expansion tanks and just how important they are and how to size them and all of that. Probably break for a quick bite like we have been doing, and then we'll get back at it and we'll finish up with a piping technique, which we've mentioned or touched on a little bit, but primary, secondary piping. And we'll talk a little bit about that and some of the applications and what you'll see in your career moving forward, especially with some of the, like what probably Will touched on last week with some of the heat pumps and some of the newer technology and working in conjunction with some of the more, what we'd call like a legacy traditional boiler plant, etc. So anyways, we'll jump right in. We'll try to jump right in. As far as air or air control or air elimination, a couple of different systems we'll talk about. Describe the pressure band, what that means when we say that range, that pressure band. Establishing the fill pressure when you fill a system. What do you set it to? How do you calculate that? When you're dealing with expansion tanks, and typically today you're always going to be dealing with some type of bladder or diaphragm pre-charged expansion tank. How do we calculate that appropriate pre-charge? Because when they ship from the factory to the job site, they are charged, but the factory has no idea what building they're going in. And so it's very specific to the site what the charge needs to be. We'll talk about that. And then we'll go through some sizing of some tanks and what's involved, what you need to do, both a little bit of behind the scenes, old school, and then what you're probably going to do today with software. But the classic, adage, garbage in, garbage out. So if you put the wrong information into the software because you just don't know, it could probably give you the wrong selection. So we'll talk about that. And then a little bit about at the end, just with the relationship of where the expansion tank or bladder tank ties into your chilled water system or your heating system, where the tank or where the pump or pumps should be located and what's the best practice and why. So it's whatever, 4, 5, 6 bullets there, a lot of information. And it's very practical. It's used on all hydronic closed loop heating and cooling systems. So air in hydronic systems, friend or foe. So there's benefits and then there's some negatives with the air. So if you have enough air flowing through a system, which you really don't want to, but you can, it can actually get into your terminal units, your fan coils, and it can restrict either flow and or output chilled water for cooling or hot water for heating. The air flowing through the piping and the valves can cause noise, which doesn't hurt the system. It's not very encouraging or comfortable for the clients or the tenants that are sitting in those offices or apartments or condos. And it can change the system pressure reference point. We'll explain that later on. Some of the benefits, we can use it to establish a suitable cold fill pressure for that system. How do we pressurize it? We use that body of air, that body of gas in that expansion tank. Most importantly, this one in the middle here absorbs the expansion of water as you heat it. So you fill a system with 40, 45 degree street temperature water, you fire up your boiler plant, it heats, you got to put it somewhere. And there's expansion tanks using this cushion of air is perfect for that application. And then the last part here, which is kind of subtle but important as well, provides a reliable pressure reference for the system. So the pumps will reference where the expansion tank ties in to our system. And in there, from that point, will dictate the pump's pressure differential, the head pressure that it can develop, how it shows up as a positive in the system or a negative, which we don't want. But from a corrosion, I mean, you can get some pretty aggressive stuff. Obviously, there's a couple of pictures of impellers at the top here. And over time, with an unchecked amount of air flowing through a system, it can wreak havoc, whether it be through cavitation, and kind of really attacking and pitting the brass on these older impellers, or even getting into corrosion with the bearing assemblies and the seals and such. So we don't want that to happen. We want to prevent that. And it's easy to prevent. We just want to make sure we do. Just a real quick old picture, very first hydronic systems here in New England, here on the East Coast of the United States, would have been what they referred to as gravity hot water. It was before pumps were developed. And they were just firing using a coal-fired boiler that would heat the water, and the lighter, hotter water by buoyancy would travel, would float, would start to move through the system. And through piping techniques and all of that, they would have circulation established by gravity. And the way to do it was to really oversize the piping, because there was no pump to overcome pressure drop. So you had to keep the resistance extremely low. And the way they did that was by oversizing the piping. So it was a big step from going from a fireplace to central heat. But from where we are today, this is obviously quite antiquated and not very efficient, but that's what they would have started with. And they would have had an expansion tank, an open tank at the very high point, top of the building, in the rafters, in the attic, as a high point. And they would use that tank to fill the system. And as long as that tank was filled, then they were pretty assured that the rest of the piping and everything below it, radiation, was filled as well. But today, everything we touch is closed. And we've referenced that expression, closed hydronic system, chilled water or heating. So we have air separation equipment. So we have venting the air on startup. And then once the system's filled and now we start to heat it, and we have air coming out of solution from the water changing its temperature, we want to remove that entrained air so it doesn't create a problem. And in addition to this requirement on the closed system air separation, we also have pressurization. So we have fill the system and provide proper venting pressure, preventing boiling. If you're dealing with high temperature water, which isn't that common, but you might get into some applications. Certainly avoiding pump problems, and then control the allowable system pressure rise. So you have a fill pressure, then you have a boiler or boilers or chillers, but they have relief valves, and they have a maximum pressure that their manufacturer says, hey, I don't want to operate in a pressure higher than. So that's my high side. So I got to control as that system pressure increases, it never approaches the relief valve setting. So closed forced circulation, adding circulators, again, almost just from a historical perspective, is these expansion tanks, they would have been called a closed steel compression tank. Old school, it was referenced under a technology called air control. And I guess the big takeaway on this, just from a historical, just to understand it, is the only vents that they had in the system were these manually operated. There was no automatic air vents, because they didn't want to eliminate it. They wanted to control it. And they wanted to use their air separator, and any air that they could catch, they would direct it up to this steel compression tank. We've moved past that. Once butyl diaphragm became a popular source, we would go to either bladder or diaphragm tanks. And we went away from that older steel tank. And that's what you're going to see. That's what you specify. That's what you'll see all day, every day. Some type of a diaphragm or bladder expansion tank. And then you can have some high capacity float vents. Still on the terminal units, you might not have automatic, you might have manual. But then on our main air separator, we're also going to have some type of high capacity automatic vent to get rid of that air, because this system was then referred to as air elimination. Any air that came out of solution because of the source of the boiler heating the water, we'd want to catch it and get rid of it, eliminate it. So that's that system. Very simple drawing, but that's the systems you guys are going to be working with, designing, specifying, etc. So just a quick discussion on the behavior or air, I guess you could say, in these closed systems. And what they're saying here is the temperature and pressure influence of entrained air removal. So if I have water at a constant pressure and I increase its temperature, it will release dissolved air. It will release air that's in solution, H2O, water. It will release some of that because it can't hold it as the water gets the temperature of the water gets higher. It will release some of this oxygen or nitrogen, technically, as in a bubble form. Another characteristic to be aware of is if you keep the temperature of the water at the same, but you play with the pressure, you lower the pressure, air comes out of solution. So if you lower the pressure on water, air can come out. If you heat the water, air can come out. And there's a relationship that exists. And that's what they're just trying to show here. In one of the booklets that you would have got on that first week when we handed out that manual, there'd be an air management manual, and they'll have this chart in here, but they're talking about the percentages. As the water gets hotter and the pressure gets lower, it's the least amount of air that the water can hold. As the water gets cooler and the pressure increases, as a percentage basis, it can hold more water in solution. When you're dealing with hydronic heating, you're heating the water. We're going to release that air. We want to catch it. So how do we catch it? With temperature, of low pressure, with low velocity, a couple of different technologies that we use on our very common and specifiable air separating equipment. So right off the bat, you fill a system, right? And as you fill it, the liquid fills piping, provided one, the motive pressure is greater than the air pressure. So as I'm taking this fill system, this fill pressure reducing valve, I might even close this and open up the bypass, and I go and I fill the system. I got to make sure that that incoming pressure can fill the adequate, 10-story building, 3-story building, whatever it is. And then obviously the motive force is greater than the static pressure. So you start getting into high rises, you might get into like jockey pumps or booster pumps that are used to fill the system because the static height is much greater than just the actual income and street pressure. That's not the common, but you get into those high rises, they might handle it differently. But we do want to have vents that we're going to vent and release that air because the piping is completely filled with air before you fill it with water. We just want to displace it all. And then you have terminal units, and they're going to have vents. And a lot of times in the terminal units in the apartments or in the condos or in the office spaces, they might be this type of version of a vent, and it's called a manual vent, where the contractor, the pipe fitter, he'd actually go over and use like a flathead screw, and open it up and release the air manually. And the point of this little drawing here is when you fill in that system, you really want these vents open. So there's going to be a handful of technicians throughout the building addressing each floor as you go from first floor to second floor to third. You want these vents to be open to displace that air, because you can fill it, have this thing closed, and when you read the pressure down in the mechanical room, you say, oh, I got to my point, I'm fine. And half the radiation is completely filled with air. That's not good. So, and they know this, but we want to open up these vents as we're filling that system to prevent air binding. This is just a quick example of when we're selecting, and sometimes it almost gets into we talked about a couple of weeks ago about control valves and the pressure drop on control valves. And we can use that pressure differential because in this example here, we have very low pressure differential across this coil and control valve. And when the pump comes on to provide the appropriate flow just through this one coil, he only needs to provide a 2-foot differential. And what this example is showing here is we could actually still have some air stuck in the coil, and the pump doesn't know it. He's just turning on, and I can create some air binding. So it's not uncommon that what we would do is we'd say, hey, the pressure drop across this coil right here, we might want to make it a minimum of 6 foot of pressure drop. So anytime it comes on and the control valve opens up, I create this pressure differential. I know I'm completely displacing any air that was in that. So just by simply turning the pump on and opening up that control valve, by having this higher pressure differential across the circuit, it purges. It gets rid of any residual air that's in that terminal unit. So this is, a little different, but that's not uncommon because, oh, I want to keep the pressure drop low and all of that. Well, that might work against us. So one of the reasons, in addition to that control valve authority we kind of touched on, is we can use it to self-purge the terminal units by making sure the pressure drop. And it's a function of, how big is that terminal unit, that air handler, that coil. So just some kind of basic bullet points, good piping designs. Avoid air traps to make sure we can ensure automatic purging at full flow. Make sure the velocity, feet per second, how fast is that water moving, is high enough to carry the air out through the terminal units and back to our air separating devices. And then obviously we just want to have proportional flow, meaning we want to balance. We're showing one fan coil here. We might have 100 or 200. We have to make sure we have proper balance so that we have appropriate flow, which means we also have appropriate velocity through all the units. So air separation. Once we're up and running, we've filled the system, we've vented it. Now we're going to engage the boiler plant. As air is released, we got to address it. We got to make sure it's not a problem. So the different pieces of equipment, and we would have touched on this very briefly on week 1, just some of the components you see in a hydronic system. But this very specifically, air separation and removal during normal operation. Where do we put the stuff? Where do we put our air separator? Where is it where is it recommended? Where the system fluid is the warmest, because based on that old chart I just showed you a while ago, the warmer the water, the less air that water can hold in solution, so it's going to come out. So when it comes out in bubble form, we want a device to catch it. So where the water is warmest and where the system pressure ideally is lowest. And air release connections, everything that we're going to talk about and what you guys are going to see moving forward in your career will be this: air elimination. So there'll be some type of vent located on top of all of these air separating devices to discharge the air out. So again, like in a hydronic system, obviously it's pretty common sense, but where's the water the warmest? Well, if that's my boiler, right, that's my source of heat. I'm heating the water. Well, before I get to my pumps and out to my terminal units, I want to have my air separating device right there, catch it, right at its source. I don't have bubbles of air flowing into my impeller, which can cause that cavitation and create unstable pump operation. So I want to have my air separator right here. If I was dealing with a chilled water system, where is the air? Excuse me, where is the water the warmest in chilled water? Because this picture on the right, what they're trying to show here is this may be a bank of 3 chillers, primary, secondary connection with their own chiller pumps, and they're also feeding all of these terminal units. So what we're showing here is the air separator, in this case, in the chilled water, is on the return. That's where the water is going to be the warmest. And as importantly, again, we'll get into it later on, where our expansion tank is connected is very important. And we're showing both bladder style and diaphragm, which we'll talk about. But so ideally where the system water is the warmest and the system pressure is the lowest. Couple of different techniques or devices, air separating equipment. Probably the least expensive and relatively speaking, pretty simple in its operation, but all they're doing is they're using velocity. And so what will happen is these devices, whether it's a little 1.25 inch here, or it's a 4-inch or 6-inch device, they'll have a pipe connection. And as we talked about before, like talking about that system size, and when you pick pipes, the sizing of the pipe, you're selecting 2 things. What's the frictional resistance? And then what's the velocity? Like on scale 2 and scale 3 on that old wheel we talked about. So typically system flow is around 4-5 feet per second. And that's good. That's all good engineering principles. The way this thing is manufactured is this diameter here just allows that 4 to 5 feet per second to drop to a 1/2 foot, 6 inches per foot per second. So it becomes like a wide spot in the river, and the water slows down. So the air that came out of solution when it came out of this heated boiler up through the supply pipe hits this low velocity area, air comes out of solution. It gives it a quiet spot. And these bubbles will then be vented off the top here with a high capacity vent. So it's just velocity. And it's so simple looking, but there actually was engineering involved to say, hey, this diameter right here will cause this 5 feet per second to slow down to half a foot per second intentionally. And then continue back on the way back out, back down to our 4 to 5 feet per second with a smaller diameter pipe. Very common, commercially speaking, would be this a coalescing air separator, or enhanced, might be another term, an enhanced air separator, but it uses coalescing medium. So what's happening here is we've got all of this surface, the stainless steel fingers and surface area, and they call it stainless steel coalescing media. But it's surface area. So you get all these bubbles coming in. A lot of times you'll hear the expression entrained or micro bubble. They're smaller bubbles. And in and of themselves, they don't have the buoyancy to float. So they'll have all of this area, this coalescing medium surface area for these smaller bubbles to gather. And then as more and more gather together, it becomes a bigger bubble and it separates. Very high efficient air separation. Same thing, located, has a high capacity vent on the discharge on the top of it. And again, located down in that boiler room if it's a hot water heating, or on the return side for a chilled water. Has a blowdown connection because we can almost use it for a little bit of dirt separating as well, connecting it to perhaps an older system that might have some dirt particles coming back. Well, as the flow again is coming back, or depending upon the direction, all of a sudden it hits this wide spot and that velocity slows down and allowing some of that dirt to collect. So they'll have a blowdown valve connection on the bottom there. Very, very popular, especially in the engineering world, the specifiable world, is this, in Bell and Gossett's world, they'll call it a roll air troll, but as a generic term, tangential air separator. And just by the design, it creates this centrifugal action. So the inlet and the outlet are actually located on the outer edge of the shell of this air separator on the same side. And then they're one's on the top inlet port and the outlet ports on the bottom, but they're on the same outer edge of one side of that shell. And so as that water's coming through at that velocity, 4 to 5 feet per second, it creates this centrifugal action. And so that water's kind of spinning, and as it does, the heavier air-free water spins to the outside shell, which is what they're trying to show here. This is a little bit of a computational drawing, but the heavier air-free water spins on the outside of the shell, working its way down through that outlet port at the bottom. And then there's a stainless steel collector tube in the middle where it's kind of slower and quieter, because that centrifugal action is taking place on the outer edges, and the air bubbles kind of gather, and then they'll typically release at the high point with some type of high capacity vent. Very efficient, been around a while, very popular in the hydronics industry. It's just it's a good understanding of just what's going on. They'll refer to it as centrifugal action. Another device that's out there, it's called primary secondary header, or a low loss header, is really, and we'll touch on this a little bit later on when we get into primary secondary connections. They actually made this device, a bunch of different manufacturers made this device as a primary secondary. But one of the side benefits was, as they engineered it, they created this low velocity area. So sometimes a contractor, or you guys might specify, you might be putting in 2 or 3 boilers in a mechanical room, each with their own boiler pump. Now I'm going to connect it to the distribution piping that's going out to feed the building. And I'll connect the 2 loops with this low loss header, this primary secondary header. So as I'm taking the heated water out of the boiler plant, and before I get out to the system pumping, I'll pass through this low loss header, and I'll collect, because of the low velocity area, I will collect any of the air bubbles that come out of solution from the heated water from the boilers, and I'll vent them out the high capacity vent at the top here. So it's just another method. Of all of them, yes,
Why doesn't it bypass?
why doesn't it bypass? Right, it could depend upon flow rates. It depends on the flow rate on the system side and the flow rate on the boiler plant side, CNO. And we'll talk about it more this a little bit later on when we get into primary, secondary. But it could, depending upon what this flow rate here is and what this flow rate here on this side. I keep saying, we're using these high capacity vents. There's all different vents that are available, price and capacity, manufacturing, longevity, etc. This guy here would be definitely deemed a rugged, robust, commercial grade, high capacity float vent. But you'll see all different types, and they're all internally, they're all very similar with the float and like a lever that's attached to a plug or a port that's going to open or close the opening here that's going to allow air as it gathers at the top. And what happens is that floats up because it's surrounded by water. When all of a sudden air bubbles are allowed or forced by the air separating device below it to force these air bubbles, well, all of a sudden the float's surrounded by air and the float drops. And as it drops, it's pulling away the plug from the port, from the opening, and what's behind that water? System pressure, pushing the air out through that orifice, through that opening. And then as it gets replaced with more system water, the float rises up and closes off, so it's not spitting water out either on the high points in the system or down in the mechanical room on the air separating device. So when you're selecting them, they'll have a couple of different things: maximum pressure, maximum temperature. So there's some things to be aware of as you're specifying air vents in a hydronic system. And again, just to kind of wrap it up a little bit, but air separating equipment where the water's the warmest and where the pressure's the lowest. That's the ideal location for these devices. And in your world, and what you guys are going to see and specify, it's going to be this coalescing medium or this centrifugal centrifugal action, this tangential or roll air trail air separator. Those are absolutely the two most popular. 9.5 out of 10 times, they're going to be line sized. So if you're dealing with a 6-inch main, you got a 6-inch air separator, 8-inch, 2-inch, etc. And the manufacturers know that, okay, based on 6-inch, you're probably dealing with X flow rate gallons per minute. We make sure from an engineering of the diameter and the centrifugal action that it can handle that flow and still do a good job of separating the air. So pressurization. So what are we talking about? Well, either just straight pressure reducing valves as you're bringing in street water into the system, and you have this pressure reducing valve that's going to knock down the street pressure to the appropriate system fill pressure requirements. Or other times, maybe it's a closed system where we have glycol. So we have a glycol makeup package with like a booster pump, and we'll be using that setting to maintain and set a certain system fill pressure. Another pressure component, if your pressurization piece of equipment, is the pressure limit component. So a relief valve. And these, kind of sit off to the side. Hopefully they're never active, which is a good thing, but they're there to protect equipment and the building and everything else associated with it. And so the relief valves are there to do it's a kind of a combination. I'm going to have a maximum pressure, operating pressure that the equipment that you've installed or specified says, hey, the boiler manufacturer says, hey, I can't operate anything higher than 50 pounds on my boiler. That's when it got tested and proved. Okay. The other part of that equation is, in addition to honoring that max pressure, what's the BTU capacity? How much heat can this thing develop? Because I got to make sure when that valve opens up, because maybe it met that max pressure, if there's something going on, I shouldn't be active, but I am for a reason. Make sure I can get rid of all of that energy and get it out of that heat exchanger, get it out of that boiler, whatever it's attached to. So straightforward stuff, but very important and hopefully never active. So the role of an air management tank can be a system pressure reference point, and we'll talk about that with regards to pump location. Retains surplus system fluid due to thermal expansion. So you take a certain amount of water when it's cold, you heat it, it expands. That's the surplus. I got to put it somewhere. Because if I don't and the pressure rises, what's going to happen? What are these guys going to do? They're going to open. What's the problem with the closed system having a relief valve open to get rid of that excess pressure? Bringing in more air. Why? Because you're going to refill it with cold water. And the cold water has what? Plenty of oxygen because it's cold. It's in solution. And then we put it through that heat source, boiler, heat exchanger, whatever, and it releases it. And you keep doing that, you can start to corrode your system, as well as the cost of water. You're bringing in makeup or you're dumping it. So we don't want, by a bad design, and that's what the expansion tank, again, one of those pieces of equipment that once if it's done right, you almost don't know it's there. And when you install it correctly and you've sized it correctly, it's almost like you don't know it's there. But as soon as you don't, or someone messes up or doesn't follow your instructions, then it becomes, all of a sudden these things become active and all of that. And then all of a sudden you don't have a closed system. You have an open system because it keeps opening to relieve pressure. Again, almost for historical purposes only, these are just some of the different components that were needed, which you can see is quite a collection of all these different accessories to go with that old steel tank. That when you look out from the inside, you can't see it because it's steel. But what would happen is this was before butyl diaphragm was available or being used. So the air and the water, the air and the water touched each other. There was no separation. So it would work, but you were definitely dotting your I's and you were crossing your T's. There was a lot of details. And some of these accessories were very important on how how efficient or effective that system was. But again, historical. You're not sitting here designing this anymore. But that would have been the first, air control. Now, this is what we're dealing with. Diaphragm and bladder tanks. A bladder truly is a bladder bag inside the internals of this shell of this bladder expansion tank. And then a diaphragm is what the expression you might hear in the industry is it's a partial or a limited acceptance. It's not full acceptance. Whereas a bladder and the way it's sized, it's full acceptance. It'll make more sense as we start applying some numbers to it. But they both work. They're both fine. Probably a little more pricey and more appropriate as you get into bigger volume systems. Makes more sense. A little smaller volume, still, commercial grade, ASME rated. They might go to a diaphragm style tank, but they both same principle. There's a diaphragm or a bladder that's separating versus the old water and air saw each other. That doesn't happen anymore. And we move to air elimination. Get rid of any air we find. So one of the comments just to be aware of, and especially if you're, specifying a tank and you're putting it in a particular system that you're designing, not a bad technique or not a bad discipline to get into is find out what the tank should be charged at. And that's up to you because you're building the system. You're going to know the height. You're going to know all of the parameters because they'll come from the factory nowadays. They come pre-charged to 40. And that can be way too high on maybe a smaller 2-story, 3-story building. And it could be way too low for maybe that 10 or 12 or 15-story building. So it comes pre-charged, but it's not a bad idea, to specify what the pre-charge is. And the pre-charge is going to be very much the same as whatever that cold static fill pressure is. And the other thing is field adjust with the tank empty to job specific cold static fill pressure prior to introduction of the system. You never want to, the contractor should not be attaching this to the system that's filled and then try to charge it if he's making some adjustments. we always want to do it before, because once we attach it to the system, now it's seeing system pressure. When you go to use like a tire gauge or some kind of gauge to, hey, what's it filled to? What's the pressure? What's the pre-charge? You're just reading system pressure. So always tell them before it gets attached to that system, just standing alone, what is it? How are you? Good. So a picture of what we refer to as a full acceptance replaceable bladder. Sometimes that'll get specified. And some of these tanks, and we'll get into it a little bit later on, but they can be huge, like bigger than refrigerators, huge. So you think about doorways and how do you get them in and how do you get them out? So sometimes if you did have one of these tanks or tanks specified, installed in a system, and then over time something happens and it develops a leak, and now you got to replace it. The selling feature potentially is, well, I don't have to physically take this shell of this tank and move it and get a new one. Maybe I can just take this assembly off this flanged top and replace the bladder. Now, us sitting here in this room talking about it, easy peasy. The contractors, the technicians out in the field doing it, it's a big deal. It's a big challenge. So it's an option, but it's not as easy as I just described. And they'll let you know, when they have to wrestle with that. So sometimes we'll get into it a little bit at the end, but maybe one big tank can handle it. But maybe the real right answer is to specify two smaller tanks that can get in easily, not take up that much space in the mechanical room. And then down the road, from a serviceability, maybe it just makes more sense, labor and time. If something did happen, I take one of them out and I replace it, just from a time standpoint. But anyways, air on the shell side, and then system connection. So system fills, and they'll have like this, they call it a dip tube or a hose that's attached to part of that bladder, that bag, so that it directs the system water all the way down. So it truly fills that bladder as that system water is entering. And why is it entering? Because you heated it. The boiler came on. The system volume is expanding. Prior to, or before the system turns on, you got to remember that whole system's filled with water. There are no gaps. Water is not compressible. You heat it, it's going to expand. And either pressure is going to take off like a rock, or you have a place for it to go squeeze against the air. And the tank is sized such that as that air is getting squeezed, pressure is rising. But we sized it so that that relief valve never even saw that increase to the point where it opened. Yeah, it's like an accordion. It's all collapsed. Correct. And that's another point. I'll repeat myself probably 3 more times tonight. I apologize, but one of the things is when you go from this style to that old steel tank that had air and water and they saw each other. So right on startup, before you turn the boiler on, there was already water in that tank. And that was just because there was no bladder. There's no butyl diaphragm to play with. So that was just how they designed it. So the tank was much bigger than when you go to these diaphragm or these bladders, because there's no water in the tank until you heat the water. And then the other thing was those old tanks, that air, because we weren't eliminating it, we were controlling it. That tank had to be installed so you could use Mother Nature. You could use the buoyancy of the air bubbles to find their way back up into that old steel tank. Here, I'm not trying to direct the air. I'm trying to eliminate it, get rid of it. So there's a lot more flexibility on how you can install it, where you can put it, as long as you pipe it over to your air. There's a lot of flexibility with the installation. So there's a lot of benefits and why we went this way. So no. Yep. ASME, right. Yes, correct. Yeah, there's a threshold where you can stay below, and as soon as you get to a certain BTU rating, the other thing they might reference is the relief valve, pressure relief valve on that boiler. If it gets above 30 pounds now, so if it's at 40 or 50, now we're looking at ASME commercially. And then you'll find out when they try to cut corners, because from an economics, from a cost standpoint, Getting a non-ASME tank is less expensive than the ASME. Makes sense. But then the insurance inspector who's writing the insurance or inspecting for the insurance company, he does his inspection and he's looking and saying, hey, that's a 50-pound relief valve on your boiler plant. These are non-ASME tanks. They're going to be ASME to meet the code. So stuff like that, 400,000 BTUs, fill pressure. I mean, yes, sir. Yeah, over 30, 30 and under. Yes. Yeah. We had a situation downstairs years ago. We had a couple of boilers that we had operating for heating as well as we used it for a little bit of educational. And the sticker from the boiler manufacturer said, I think it said up to 50 pounds. So the boiler was rated up to 50, but we were only using it as a 30 pound. It had a 30-pound relief valve, but the sticker said 50. And the inspector caught us and he was like a stickler. He said, hey, you either got to change that diaphragm tank from a non-ASME to ASME, or you got to get new. So we reached out to the boiler manufacturer and said, hey, can you send us a new official label from you that said 30 PSI? So they, you'll see it commercially, they'll see it all the time that they pay attention. Manual resets on boilers have to have that manual reset button. You can't just have a auto reset low water cutoff. You have to have that manual reset. So they go around the mechanical room and they look for, things. So anyways, so the allowable pressure range. What system pressures are we talking about? So it's kind of like it's building blocks. So just be patient with me as we walk through because it's pretty basic, but you just want to be aware of it because it's the building blocks for as you looking at systems and designing and then working backwards and perhaps troubleshooting. So what pressures are we talking about? Well, the first one's going to be what's our initial cold fill pressure, right? So you look at this very simple drawing here. We got a boiler. We've got what's missing, but should be an air separating device, and then our expansion tank connected. We've got a distribution pump feeding a piping system back to the boiler. Very simple. And they're getting very detailed because a lot of times when you talk about these things, you'll say, hey, the fill valve, the relief valve, the expansion tank, they're right there. They're all in the same plane. We're not doing this. But here they're kind of getting a little specific. And they're saying, okay, safety relief valve outlet. So the R dimension is from that outlet to the top of the system. The L is, okay, the height of the system to the pump suction. The D is from a fill valve up. And our H is where our expansion tank connects. In our world, most times they're all in the same plane. That's what, there's not enough of a difference to make a difference. You're talking less than a pound or whatever. But just for technicalities, they're separating them to spell it out for us. So they're saying, okay, cold fill pressure, the cold static or initial system pressure. What's its job? How do we establish it? What is it? We got to fill the system with water. I mean, it's simple, easy. Fill the system. The other thing we want to make sure is that if we have any kind of venting requirements at that high point, which is not unusual because all things being equal, if I do have some little air floating around, where's it going to find its way? It's going to go to the high point, right? Eventually, it's going to find its way. It's going to float to the highest point. So typically, I'll have some type of venting capability, whether they're manual or automatic at the high point. And then this last thing, not that common, but maybe avoid some pump problems. So just real quick, very, very simple, little two-story house perhaps. But we're applying some numbers and we're saying, okay, from that PRV valve up to the first floor, then up to the second floor to the radiation, and then to the top, because we've got radiators like these guys, radiators as opposed to maybe baseboard on the floor. You put some numbers to it and you say, hey, do the math. 18.5, 3, 13, 15, 18, 18 and a half divided by, to convert to PSI, I need 8 pounds set at the PRV valve. And if I set this at 8 pounds down here, I've got water to the high point. Now, here's one thing just to remember. At 0 pounds, I've done the math. I've got it all the way up there. But what pressure am I at the top? 0. So if I was to open up a vent or if I had an automatic float vent and the system pressure on the inlet of that vent was 0, and I'm going to atmosphere, which is 0, there's no motive force for the air to move through the vent. So when they make kind of a silly little statement and they say, hey, provides venting pressure, that's what they're referring to. So whatever it takes to get there, 8 system are kind of like an industry standard, add 4 to 5 pounds. And all you're doing is at that high point, I'm not at 0 anymore, I'm at 4. So now if I have some air bubbles with a vent, I've got 4 on one side, 0 on the other. It's not a huge differential, but it's a differential. Air will pass through that float vent. So it's a positive. So now I'm going to set downstairs here that PRV not at 8, but at 12 or 50 or whatever the height of that building is. So it's a function of just the height of where you're from your feed valve, your pressure reducing. They're making the assumption the mechanical room's down in the basement. What happens if you had a penthouse up on the top of a 10-story building? What would your fill valve be set for if you're at the very top? You can make it as low as you want almost. Like a lot of times they come out of the box set for 12. You just leave it at 12. So it's 12 at the high point because it's going to fill that entire system. The other benefit of sometimes putting that mechanical equipment up on that high point is what's the pressure on the relief valve at that high point equipment? Back to your 12, 8, whatever you set it for. Versus you take that and you bring it downstairs, and all of a sudden you get all the weight of the system sitting on the relief valve. So now you're looking for a much higher rated equipment, relief valve, ratings on the boilers and bigger expansion tanks and all that. So just things to be aware of, that static pressure and what it can do. So when we get into that allowable pressure range, and what we're referring to is here, we got to set it because we got to make sure the water's at the high point. We're circulating water, it better be there to deliver cooled water or hot water. But then we have this safety relief valve that's there to protect the equipment, but I don't want him active. So here's my range. That's my allowable pressure range. I can let the pressure rise, just don't get to my relief valve setting so it opens and discharges. I want to prevent that. So standard conditions, and what you guys are going to get involved with is anything but standard. But just as a building block, as a starting point, a 2-story application, standard conditions, I might have a 12-pound fill, but 30-pound relief. I'm just using water. The tank, in this case, it was using an old style tank, might be at 0. But I have a PRV, a relief valve, tank, and pump roughly at the same elevation. There's not enough of a difference. So kind of an interesting thing, what's going to happen here with the expansion tanks, just as a general statement. At a constant temperature, the volume of gas is inversely proportional to the pressure exerted on that gas. So what they're saying here is when the system's cold and I pre-charge the tank, and to your point earlier, I don't want system water in this tank until it starts to heat up. That's how it gets sized. We'll talk about that in more detail. But now as the water is heating and it's expanding, it's going to go to the only place it can because water is not compressible, but a gas is compressible. So I'll squeeze that air. I still have the diaphragm separating the two, but I'm squeezing. So as I'm squeezing, I'm changing the air volume, which means I'm changing the pressure. So the volume's getting a little smaller and the pressure's going up, which is fine. That's its job. The whole key is at the end of the day, as that pressure rises, we just want to make sure we stay below the relief valve setting. So volume goes down, pressure goes up, and that's normal. That's fine. It's just it's a function of, okay, make sure this guy here is adequately sized for your particular system so that as that pressure goes up, it stays below your relief valve. Yes, Oh, How do I know if it failed? What? Yeah, the bladder breaks or whatever. Well, the first thing would be that the relief valve's going to let go because there's no place to expand. So it's like becomes a big pipe because the cushion of air is gone. Now it's filled because what would happen is as it breaks, ruptures, air gets released, system pressure drops. So now our feed valve senses a drop in pressure and brings in more makeup water because you told me to be set at 12 or 18 or 25 or whatever it was. So it brings more water in, and all we're doing is filling this big wide diameter piece of pipe. So now when I go to heat that water, I have no room at the end, the relief valve blows. Now you could say, hey, what's going on here? The key is the way the tank is connected to the system. I want to be able to valve it off, so I'm not reading system pressure. Then I want to have a purge valve, so any pressure here, I can get rid of it. And then I'm going to put, if it's a simple little diaphragm like this, I might put something like almost like a tire gauge, just to. But as soon as I connect it, if it's busted, it's water coming out because it should be on the air side, should be air charge. So the symptom will be the relief valves dumping. To confirm that, hey, I did lose the bladder, it got busted. Isolate it, check the pressure. You put your tire gauge and water comes. We need a new tank. Something happened. Or just time, maybe just, age over the time. The flexing of that butyl just finally gave out. But it would take time. It's not 3, 5, 7 years. It's over time. So pre-charge, kind of leading right into it. What's the big deal? So sometimes we get the calls downstairs. As a customer service department, we sell commercial ASME tanks all over New England in commercial settings that get specified by your firms. Back to it ships from the factory pre-charged. If the installing contractor, mechanical contractor is not aware of what we just talked about or isn't directed, he might not know enough to make a change. So what they're saying here is a quick example is if I had the tank installed into a system and I didn't address the pre-charge and it was too low, what can happen? So I have this tank and I've attached it and the system is empty. So again, simple little drawings, can be a big commercial system, doesn't matter. Now I fill the system, but the overall system volume increased. And because this pre-charge was less than the fill pressure, water starts to enter into that because it's gonna, hey, I'm greater pressure than the pressure on the pre-charge side. So I'm gonna start to displace and I'm gonna start to take up some room here of water. And I haven't turned the boilers on yet. This is cold water. So fluid enters the tank on pressure difference, not thermal growth. So the available acceptance volume, which is a key sentence we're going to get into very shortly on how you size these tanks, all of a sudden decreases. Now I don't have as much space. So then the tank air pressure, yeah, if I was to put a pressure gauge on it, it will equal the initial fill pressure, but that's because I'm squeezing the air with some additional system water that's cold that doesn't belong in there because I didn't properly recharge it so that the cold water couldn't get in. Now you go and you fire up your boiler plant. Now you go into full expansion, full thermal growth, and the tank rated acceptance volume can be exceeded. So I have this 1,000 gallons. I heat it to whatever 220, and I have 35 extra gallons, and I'm trying to put it into a tank, but I already put a certain amount of cold water. So now I don't have the 35 gallons available to me. And what will happen is two things: either the safety relief valve, so the pressure relief, discharges, or if it's severe enough or over time, that diaphragm or bladder can rupture. So by undercharging it, you're exposing it to all of this excessive pressure. But the first thing that will happen is the relief valve discharges. So we get the call downstairs. Hey, we just started up this brand new system, blah, blah, blah. Been working on it for the last 3 to 5 months. Now we turn it on, heat everything up. Relief valves are leaking on the boilers. There's something wrong with your expansion tank. That's usually how the conversation starts. Something wrong with you. And we're like, okay, that can happen. Before you attach the tank, what'd you set it for? Silence, because then, well, the factory sent it to us. The factory said it. And unfortunately, the factory doesn't know where it's going. So it's really responsibility. So what we kind of subtly harp on in these slides is, as a specifying engineer, if you could throw it in the drawing, hey, this is going into this tall building. It's going to need this fill pressure. We know the mechanical room's down in the basement. Make sure you pre-charge your tank to bleh, whatever that bleh is, 35 pounds, 42 pounds, whatever. While it's not connected to the system, pre-charge it. Then some of those calls go away. Yeah, that 2.3 feet height per inch, right? So that's my pounds per square inch pressure. So if I'm, especially the smaller residential ones, they only come at 12. The commercial ones are now coming at 40. But yeah, it's a static weight of the system water. So on the height of the building. So then guys will say, they'll get cute and they'll say, you know what I'll do? I'll beat the system. I'll overcharge. I will pre-charge it too high. So now I've got the safety factor. And so again, system empty, pre-charge the tank to more than what I needed for my PRV valve. Overall, so I fill the system. Overall system volume unchanged, tank acceptance volume. I haven't put any water in here because it can't, because I overcharge it relative to the fill pressure requirements. So you think, well, everything's good. But now you start to heat the water. It's not full on, but it's starting to heat. But that expanding volume can't enter the tank until the pre-charge pressure is exceeded. So as I'm starting to heat up and I'm starting to fill, I can't get in here until this pressure here is greater than that pre-charge, that I overcharge it to cheat, like I'm going to beat the system. But still, the same thing can happen where the acceptance volume reduces slightly, but the tank air pressure has raised up to or even above the relief valve setting. So it's not so much that you're going to probably damage or rupture the bladder. You're just going to open up the relief valve and you're going to get weeping. So the point of that whole story is, don't undercharge them, don't overcharge them. There's a right charge. It's a function of the height of the system when it's cold, so that when you fill the system cold, no water enters the tank. And then as we get to these exercises on sizing the tank, we know that we've got X number of volume of water. And when I heat it to the maximum temp, I know what the volume, expanded thermal volume is going to be. I've got the tank or tanks there to support it. And again, like I said at the beginning, when all of that takes place, these guys sit off to the side like they're not even there. They're like, we don't even know. But as soon as they're wrong, then all these other things start happening. And it's like, hey, what's wrong with your, but so how does pump head influence system pressure? It's just a real quick, it's that last one, cold fill, operating pressure, increase, heat. The last one would be I turn the pump on. So I turn the pump on, system pressure is empty, pre-charge the tank to whatever that height of the system is divided by plus my positive pressure. I adjust my fill valve here, my fill valve. Again, we call it all the same, but they're saying, hey, L is different than D, different than H. Technically, there's different heights, but you set all of these. And then if I fire the boiler and I have the pump off, I'm going to see this thermal expansion and I'm going to have water entering into the tank. And as long as it's sized and pre-charged properly and sized properly, the pressure increase is going to happen, but it's not going to activate. It's not going to cause my relief valve to dump. And then if I turn my pump on, right, this design temperature and then pump on, the gauges are going to be whatever that system pressure was. And then I'm just adding one other additional thing would be the pump head. Can this develop 25 pounds, 2 feet? You know, how big of a pump, how small of a pump? It'll show up on the discharge of that gauge. From a visual, look at it this way. The red is that system pressure with the pump off. And then when I turn the pump on, whatever his differential, I don't know why it's saying green, it's blue, but whatever that differential is additive to the system's fill pressure or system pressure. So the blue is representing the pump's pressure differential. I stated up here, it says all the pump head must be used up. So as the greatest differentials right here, why is that dropping in pump head pressure? What's happening? Friction. We're eating up the energy, which we sat on week 1 saying, hey, what's the flow rate? What's the size pipe? What's the pressure drop through that loop? Okay, I got to buy a pump that can do this many gallons a minute and create this pressure differential. And when I turn it on, everything being right, my greatest differential is right here. But as that flow takes place, there's frictional resistance that's consuming, that's eating up the energy that pump could develop. Another point, or another subject, I should say, called the point of no pressure change. And I mentioned the guy before, this guy, Gil Carlson. Great picture of him. And I don't know if I mentioned this before, but before he passed away, and unfortunately he passed away a while ago, someone was smart enough at Bell and Gossett, and they brought him into their little red schoolhouse, which I think I mentioned, maybe showed some pictures or whatever. And they sat him down and they said, hey, Gil, we want to videotape you. Let's talk about all the different things you developed and promoted in the industry to the engineering community and all these different functions and designs and primary, secondary circuit setters. He developed all of these things. So one of the things he did was he created this comment or this phrase, point of no pressure change. And so they videotaped him, and I just took a screenshot of it just to say it. But he talked about where the pump's located in the system relative to where the expansion tank ties into the system will determine when that pump turns on, is his pump pressure differential that I just talked about, is it additive to the system? Or sometimes if it's in the wrong location, that differential here will be negative. It'll drop, which is crazy, but it can really create operational problems. And so he talks about, and he actually wrote a paper and sent it to the engineering community through ASHRAE years ago about this proper pump location. So really very simple. What this is why why it is what it is, if you will. So we're saying, you know, very simple little piping connected to an old style, because when he wrote the paper, old tanks. Today we'll replace it with a diaphragm, and it's the same principle. And what he's saying here is, I got this system completely filled with water and a pump and my expansion tank. And he says, if I was to draw here and I was to put a boiler there and I turned the boiler on, so the boiler started to heat the water, what would happen to the volume of the water in the system? It would increase. And where is the only place that volume of water could go? Where the gas is, right? Because I can squeeze the gas. I can't squeeze water. It's not compressible. So as I enter that additional thermal growth of that water, I squeeze the volume of air, which means I change the pressure. Because as you change the volume, you change the pressure. We just talked about Boyle's law, right? As I make the volume of air a little smaller, I'm increasing its pressure. I've changed the pressure. So he says, okay, take the boiler, take it away. Now go over it and say you draw in, say, a fill valve. Just what we talked about, pressure reducing valves, and you opened it up and you added more water to a system that's completely filled with water. Where's the only place that additional water could go? Just like we said, it would go to the tank. And then going to the tank, it would change the ratio of the volume of air, which means it would change the pressure. So if I heat the water or I add water, which means I can change the volume of air, I can change the pressure in the tank. Then he says, this one's no heat, no pressure reducing valve opened, just a closed system. And now I simply turn the pump on. By turning the pump on, do I change the volume of water? Can't. So if I don't change the volume of water, I can't change the volume of air. So I can't change the pressure. If I don't change the volume of water, I don't change the volume of air, I don't change the pressure in this tank. If I heat the water, I'm going to change the pressure because I've added water. If I open a feed valve and add additional water to the system, I'm changing the volume. I'm going to change the volume of air. But if I don't have those two things going on, I simply turn a pump on, I can't change the volume of water. I can't change the volume of air. I can't change the pressure of the tank. And that's the paper he wrote to the industry saying, it's very important where you put this pump relative to where this tank connects. Because if I'm pumping at, again, back to that point of no pressure change, if I'm pumping at this connection, I can't change the pressure in the tank because I can't change the volume of water, which means I can't change the volume of air. But I'm a pump and I'm going to create this differential, this pressure differential. So in this orientation with this arrow saying, hey, I'm pumping that way, if that pump came on and you had gauges on the discharge and gauge on the suction, you'd watch the suction pressure drop by a function of whatever the pump could develop, whatever the pump head was. Because the discharge really is locked because he can't change the pressure there. So yes. Correct. You always want it so that the expansion tank was on the suction of the pump. So then I can't change the pressure at the suction of the pump. So any of my differential is always going to be additive, positive. So I positively pressurize that system all the way through. And like this quick slide shows, I positively pressurized it. It dissipates that increase because the frictional resistance is being consumed, but I haven't at any point in the system lowered it. It's still positive. It's just the amount of positive increase decreases as that system eats up the frictional resistance of the pump head that the pump developed. So always pump away is you hear the expression in the industry, pump away. Well, what we're talking about is pump away from the point where that expansion tank ties into your system. So we start looking at commercial drawings and the systems that you guys have, with your air separators, your expansion tank, your base mounted pumps, say, for example, you're going to almost always see that tank ties in right near that air separator. And then I go to my suction of my pumps and I go out to the system. Perfect. It's exactly what we want. Yeah, NPSH. Right, right. We want to positive. We don't want to create cavitation by lowering the available NPSH. Correct. So point of no pressure change. Yes, yes, yep, and the wrong. No, it still create the differential. It would create pressure differential. So in a closed loop, it's like sometimes you'll hear a different expression, but the pump in a closed loop system is a pressure differential machine. Just creates a difference in pressure. So I put it in the wrong place like this, and we determined that we needed 50 feet ahead, for argument's sake. And in this orientation, that 50 feet, if you had gauges on the suction and the discharge, and here's my expansion tank, would say, hey, that 50 feet, divided by 2.31, call it 22 pounds, whatever the number is, that would be additive. And then that 22 would slowly be dissipated down to 0. Not 0 pounds gauge, but 0 pressure differential, 50 feet. I mistakenly put it on the return so that I'm pumping at the expansion tank. If I put a gauge here, the discharge would stay at the pressure of the fill pressure of the system, and the suction pressure would actually drop by 50 feet. So it still creates that 22 PSI differential. The problem is, if I lower that system pressure enough, I might have float vents, say at that high point, and they're under vacuum. They pull in. and they're pulling air into the system, and they're creating air gurgling, air binding. And this is why he wrote the paper years ago, is the guys didn't know any better because it was all in its infancy, these hydronic systems as they got bigger. So they're putting these big ass pumps on the return because residentially they were putting the smaller pumps on the return and seemed to be working. They put them on the return, and all of a sudden they get sectional cast iron boils corroding because of oxidation, because they're bringing in so much oxygen every time the pump turned on. And if it wasn't that aggressive, it was just the air binding or just noise, the gurgling of the air. Or to your point, all these ear bulbs get into the suction of the impeller and they can cavitate because all of a sudden the pump's trying to pump air instead of water. So there's a lot of negatives. And to the point where he wrote the paper saying, look, you have to locate that pump so that connection of that tank is on the suction side of your pump. Now, again, these are simple little drawings. You guys will have, a little, obviously much more elaborate, but at the end of the day, when you break it down, it's going to look like this. You're going to have some type of air separator. Your line from your bladder tank's going to be right near it. And then you're going to go to your, 1, 2, or 3 base mounted pumps that are, be pumping in parallel and out to your buildings. But it's very important. And it's been known for a long time, but it's good to know why. When someone says, hey, put the pumps on the supply away from the expansion, well, why? This is it. I can change the volume of water. I can change the volume of air. Simply turning a pump on in a closed system, not heating it, not adding makeup water, just turning the pump on. I can't change the volume of water, which means I can't change the volume of air, which means I can't change the pressure. So the pump truly looks for that expansion tank. And one of the comments that was made earlier is we use the expansion tank as a pressure reference point. That's what we're referring to. The pump references the expansion tank connection. Do I add my differential as positive, like this, or do I lower it like this? The pump doesn't care, doesn't know, but it's a system pressure negative impact by locating it here that we want to avoid. Vacuum, vents draw in air. Depending upon the temperature of the water, you lower the pressure enough, you could actually cause the water to boil and create a problem. It's high temperature water, but whatever. We don't want to do this. We always want to do that. Craig, can you do me a favor? I just want to know in terms of last week, I think we do really have lobsters coming, right? Isn't it? Yeah. Make sure the butter's drawn and all that. Okay. So expansion tanks, right? Really important. Kind of elusive sometimes or sit off to the side. Very important. So what information? What's the fluid? How much? What's the volume? What's the temperature when it's cold? What's the temperature when it's operating? What's the fill pressure? What's the relief valve? So temperature in and, beginning and end, fill pressure and relief, and what's the volume? Oh, I thought just before we have a break for lunch, we should probably do a little math formula. And this is insane, but this is what he would have worked on years ago. And they got into like, as the tank gets heated, it expands. Not even less than, but they would account for. They were talking. So he said, "Look, let's make some assumptions. Let's soften that equation. Isothermal, constant temperature, expansion of the tank and the water can be ignored because there is a difference, but is it enough a difference to make a difference? And that would kind of be his go no go point. Air cannot escape. System fills slowly. Ignore volume of air liberated during heating." Trying to simplify it. So all of a sudden the equation becomes something a little more manageable. Good. Okay. So here we're saying I have an expansion factor. When I heat the water from X to Y, so in this case, 40 degrees to whatever the number is, there's going to be an expansion factor that they've already calculated. And I want to take that expansion factor and I want to multiply it by the volume of water. So if I have 1,000 gallons and I heat it to X, I know when I heat it to that number, I'm going to have 1,000 plus. Now I got to put that plus into the tank. So that's the beginning of how do I size the tank. So I need to know the volume, system volume, And that's why I want to know what's we started here. Temperature at operating conditions. That's what's going to influence the expansion volume. How hot does the water get? And then fill pressure and final tank pressure, which is really a pressure just below the relief valve. So I keep the relief valve closed, and that's where that relationship comes together. So that when I do my job and I turn my heating plant on and the tank is sized properly, yeah, the pressure you can watch on the gauge is rising, but it never got to the relief valve setting. So it stayed closed. And then when the system shut off, the water cooled down, the heat went away, the burners turned off, and the water contracted. And then all of a sudden the pressure dropped, and we're back down to our fill pressure. And so somewhere in between. So real quickly, just applying, this is just, we're going to get to the software because that's what you're going to live. That's what you guys live and die with every day. And it's easy and it's quick and it's good. Just know what you're putting in. So again, 9.5 out of 10 times, relief valve, fill valve, tank are going to be right beside each other. But they're just doing this little math problem, separating them a little bit. And they're saying, hey, I'm going to take away the guesswork. We got 2,600 gallons of water and we're heating it to 160. We have 4 pounds positive pressure and my relief valve on my boiler, maximum is 50 PSI. So then I say, okay, the fill valve, what do I need to set the fill valve for? Well, it's a function of the height. So 60 feet plus to the tank, and then an additional 9 to the fill valve, 69 divided by 2.31, 30 PSI. I want 4 pounds at the high point, so add it. So now pressure reducing, boom, set for 34. I know the number. Now, as I'm out in the field, this is getting real technical, kind of a pain in the butt, but what it's saying here is this is going to be set, but the gauge that I'm referencing to where I set it, there's a difference in height here. So I just want to account for that difference. So they're saying here, in this example, from here to the top of the boiler is 6 feet, an additional 4 feet to the gauge, so a total of 10. It's getting nitpicky. 10 divided by 4.3. So the gauge is below, so I want to add. So technically, when I reference this gauge as I'm setting that valve, it should be somewhere around 38, 39 pounds. When I read that, I know I'm all the way to the high point and I got 4 pounds of pressure. Positive. It's all good. And then I want to charge the tank, and I want to do that before I connect it, prior to installation. That's key. Height from the tank, 60 feet, 26. Pressurization at the top, 4. So the tank needs to be pre-charged to 30. Physically, because he's a little bit higher, he's not all the way down here. But in reality, a lot of times, like I said, they're all right beside each other. So they all become the same number. So then maximum tank pressure. So this one gets a little confusing. It can be. It shouldn't be, but it can be. So what we're saying here is, okay, the relief valve. As the volume expands and the pressure rises, I got to make sure that that stays closed. That's like the top of the rail. I can't go past that. So what am I doing? Static height above the relief valve is 75 feet. How did I get that? 60 plus 9, 69 plus 6, 75. Divided by 32 point. Is there a way of moving that? An hour and a half into the presentation? It's just driving you guys crazy. Sorry. So 75 divided by 2.31 is 32.5. Positive pressure, 4. So the initial total system pressure of the relief valve is 36. Now he's going to relieve at 50. Industry standards say the relief valve will start to weep before it gets to 50. So what we want to do to protect ourselves is we derate the valve by 10%. In this case, we take 5 pounds off it. So we say maximum pressure should be 45. As long as we stay there or lower, that valve's not going to open up. So this is my range. My initial pressure, 36.5. And I can let the pressure rise, but I can't get any higher than 45. or I'm going to start to open up that diaphragm. I'm going to start to leak water on the floor. And so this whole exercise was a waste of time. I still opened the valve and I don't want to. I want to have the right size tank. So maximum increased pressure, 45 minus 36.5 is 8.5 pounds. So the maximum tank pressure is the initial pressure plus the pressure increase, which is 30 plus blah. So the maximum tank pressure can only go from 30 to 38.5, which when I relate to it down here, my relief valve will climb, but it won't get any higher than 45. So it keeps the valve closed. Oh, did I think I touched this? Right. Yeah. So then acceptance factor, we start to apply and we're saying, hey, I got to establish what that acceptance factor is, and it's a function of fill pressure and then the final tank pressure. And so when I apply these two numbers, my initial fill pressure, which is absolute, so I'm accounting for atmospheric pressure, plus the 26 and the positive 4 pounds. And then my final tank pressure, which is absolute atmospheric, 4 at the top, the 26 pre-charge, plus the allowable increase to keep that relief valve at 45 pounds or under. These are my two numbers. So I apply it to this formula right here. And I come up with a factor of 0.16. So I'm going to take my 2,600 gallons, I'm going to times it by the expansion factor, which means I'm going up to 160. So when I take 2,600 gallons and I heat it from 40 to 160, it's going to be something greater than 2,600. And I'm going to take that number, I'm going to divide it by this acceptance factor. And that's going to become my total tank. So that as I accept the expanded volume, pressure rises, but it never gets above 45 pounds on the relief valve, so the relief valve stays closed. So this is the long way. I'm driving you guys crazy, I know, because software, it's quick, quick, quick. But you want to know what you plug it in on the software so it'll give you the right answer. So here's just going off a graph. You know, the computers, the software will plug this all in for us, but it's an expansion of net expansion of water. And it's saying 160 is about 2% increase in volume. So if I took 2,600 gallons times 0.02, I would have 52 gallons. So when I heat that water to 160, I'm going to have a 2,625 gallon, 52, I mean, gallons of water. I've got to have a place to take this 52 gallons. And then the last part of the equation is, what's my acceptance factor? Well, I'm taking that 52 gallons of expanded water and I'm dividing it by the acceptance factor. So now I'm saying I need a total tank of 325 that can accept the 52 gallons of water, but keep the pressure between 38.5 and 45. So now I do that and I start looking at, okay, what tank do I need? Well, it's going to get pretty big pretty quick. So in this case here, I'm saying, hey, if I did a bladder style, and these are the requirements that I'm trying to meet, and it's full acceptance. So I have to accept a minimum of 52 gallons, but I need a total tank volume of 325. Well, tank and acceptance, the first tank that I come across is quite large, a B1400, but that will meet my 325. Okay. So that'd be a solution. That's a big tank, but that's a solution. If I went to a diaphragm instead of the bladder, I could get to this D260, but notice I need two of them. And that's fine, but just recognize that you need two of these because the total tank is only 158. So I'm going to double it by having the two tanks there. So that's what's going on. Now, take away all that math and just sit there with the software sitting at your computer at your desk or on an iPad or whatever. Because we represent Bell & Gossett, we'll have Bell & Gossett's version of software. They call it System-Wise, ESP, Equipment Selection Program System-Wise. And there's a whole selection of pumps, suction diffusers, etc., triple duty valves, and you highlight expansion tanks and you click on it. And then you have HVAC tanks, which is what we're talking about, or you could get into plumbing tanks, which could be potable water for like domestic water, where you're heating water and you have backflow preventers, right? So you have backflow. So once cold water comes into a commercial, any building, it can't go back. So it's a check valve. So as I heat stored water, it's going to expand. Years ago, before backflows, that expansion, that just pushed that water right back onto the street. And it was fine. No one cared about it. But eventually the plumbing code said, hey, once the water's in your building, you have it. You own it. Don't let it back on the main. So as soon as they introduced that backflow, which acts like a check valve, people were calling saying, my hot water heater, I mean, it works. I have hot water at the shower and all that, but it's dripping water on the floor. Like every morning when I get up at night, in the morning from overnight, there's water on the floor. So what's happened is someone takes shower, does dishes, whatever, heat the water or use the water. Now they got to reheat it. They go to bed. Everything closes off. There's no more draw. And the water that's in the tank heats up. It expands. There's no place to go. Because the check valve that would historically would have let it get back on the main because the pressure would be greater than the 40, 50, 60, 70 pounds of street pressure. If I'm at 100, but I'm still below my 125, I would go that way. I introduced this check valve. All of a sudden I got leaky relief valves. So they come up with these potable domestic water expansion tanks. Same concept, it's just for that. And then the last tank over here would be well water. You would deal in, if you have water coming from the house through a well with the pump, you'd have a well expansion tank. But over here, HVAC for our heating and cooling. So here, what I've done is I've plugged in and I've said, look, I started with a 40-degree water and I heated it to 160. That was the conditions we worked with. Fill pressure was 30 PSI. Max pressure at the tank, we said, was 38.5, call it 39. The volume of water was 2,600. We were just using water. Boom, it spits it out. I need a tank, minimum tank volume of 324.5 and an acceptance volume of 54 because it's getting technical. So instead of 52, it's 54. But that's spit out. But you need to know these answers. The 30 tank pressure, the 39 maximal. You need to know what the volume of what. So these are the information. So software makes it incredibly easy, but you need to know what's going in, how you fill those numbers in. And then you pick it. And then it spits out, a portion of that software would say, hey, these are all the tanks that meet this requirement, the 325 and the 54. It could be back to that one. What the hell's the model number? B1400 that we talked about, 280s. So it gives us a list of all these different tanks. What happens if the system fluid changed to glycol? It's got a different expansion factor. Say it again. Much greater, right? So right here, and all I've done is I kept everything that I calculated the same, but I said the mixture of the glycol, because I said over here, system median is no longer water, it's propylene glycol. What's the mixture? 30%. Oops, 30%. Now it's 558, almost 560, and 93 gallons instead of the 54. So it's quite a bit difference. So now select. Now I need a B2500. Went from the 1400 liter to the 20. I mean, good sized tank. Or go to, if that D280, the diaphragm style, which before I needed 2, now I need 3. So it's just things to be aware of. But the software will do it for us. And then these are just other considerations. Will a single tank physically get into that building? Under brand new construction, yeah, because there's no building. But eventually service and serviceability down the road, how much heavier are those tanks? You start looking at the weight of these things, the dimensions, and 680 pounds, 1,150 pounds, 1,400. You get some serious weight. So these are the things to consider. And the diameter, 36 inches versus 48. Trying to get through a doorway, that might be a challenge. Then you look at the height, oops, the height of the tanks, and they're, 8.5, 7.5, whatever the numbers are, feet. I mean, they're good sized tanks. And then the last part is the weights that you're dealing with. So things to be aware of. So what have we learned other than you're starving? Keep your air separators at the warmest water and ideal with lowest pressure. Good coil piping keeps air out. The larger the allowable pressure range, the smaller the expansion tanks. That's one thing I didn't say. That example they just walked through, we had a 50-pound relief valve. What happens if I could convince the boiler manufacturer, hey, do you sell a 75-pound valve? Now I have a broader range. I can use a smaller tank. So those are things to consider. Where is it going to be located? What's the weight of that water? If there's all this pressure, can I increase the relief valve setting? So now I have more of a range of flexibility. I can use smaller tanks. Technical, but pre-charge before installing. Now that's not what you guys do. That's what the mechanical is going to do. But if we write it somewhere, say, hey, pre-charge it to this and do it before you install it, you give them a pretty good chance. Best practice to pump away from the point of no pressure change. That would be what the software looks like. You go to FIA's website or directly to B&G, you go to selection tools, and like I said, pumps, suction diffusers, triple duty, all these different heat exchangers. Probably Will talked about heat exchangers last week a little bit. But the expansion tank is one of those tabs. When we stop and get going here, just press on for the last half of this session, week 4. And it has to do with the subject of primary, secondary pumping. And so just a couple of bullet points, a little bit about primary, secondary circuit configuration. There's another concept called variable primary, which we'll just touch base on just so you're aware of it. Some of the terms you might hear are closely spaced tees, a common pipe, a decoupler. And then the last thing, we just go through an example that we actually got involved with fairly recently with one of the larger engineering firms. So an everyday project today using primary, secondary to incorporate, various new technology, heat pumps, chillers, as well as a boiler plant using primary, secondary. So just a real quick, what is primary, secondary? Very simple, very basic and effective way to distribute heating or cooling with minimal flow issues. Kind of a vague statement, but the point being here, this is what we're trying to show here is we've got a couple of boilers, each one with its own boiler pump, and connected over here, we've got, in this case, up to 4. Maybe 3 are running in parallel and the 4th is a standby, but we'll get some serious pumping capabilities here, as well as our individual boiler pumps. And this statement right here with minimal flow issues, we want to try to allow the boiler pumps to do their thing for the boiler plant and the distribution pumps to deliver, in this case, heated water out to whatever, other buildings, other areas, other terminal units, and to kind of do it without either pump knowing the other pumps are there. And the way we do it is this little subtle piece of pipe here called a decoupler bridge, or a primary secondary decoupler bridge. And it's just it's a low pressure drop area that's decoupling 2 different circuits, if you will, a primary circuit and a secondary circuit. Let's see here. Just another quick example. Instead of this, you'll hear the expression primary, secondary, tertiary. And all that's referring to is, perhaps we'll call the chiller plant the primary with its own pumps and a closely spaced or a decoupling bridge. Then we'll have our system distribution, our secondary pumps. And then this tertiary would be, a third zone, if you will. And this could be other parts of a building. It could be other buildings, plant, chiller plant, feeding buildings. Once they get into the individual buildings, they'll have their tertiary pumps that are feeding their zones, their terminal units. And each one has its own decoupler. So the Chiller pumps are decoupled from the distribution. The distribution is decoupled from the chiller, as well as the tertiary or the zone pumping, the building pumps, with their own decoupling bridges, if you will. It's kind of interesting. A lot of the manufacturers throw this information in all of their installation manuals. And so here's just real quickly, this could be a X number of million BTU Crest boiler. Just happens to be Crest where Lochinvar. Could be other manufacturers. You look in the installation manual, they're going to show the same thing. But right here, how they connect this boiler to this distribution main, or in this case, I guess it's going this way. And the boiler has its own boiler pump. And then you've got your distribution pump. You know, simple drawing could be several pumps and all of that. But they have this little statement here, 12-inch maximum. So just kind of highlight it. So they're saying the two T's that are connecting the boiler to the main are connected with closely spaced T's. And that little pipe right there is like almost like a common pipe, or a decoupler is like kind of a fancier term that's evolved over the years. Radiant manufacturers, radiant tubing manufacturers, a lot of manufacturers, well, not a lot, but there's enough of them. PEX tubing, polyethylene, cross-linked polyethylene piping. And they're doing snow melting, and they're doing radiant in homes, and they're doing radiant in commercial settings. But my point being that in their installation manual, where they're talking about using, say, a three-way valve with a system pump connected to a boiler loop, they're going to say, hey, connect this radiant loop with my heat source through this note 1. No more than 4 pipe diameters between the T's and the boiler loop. Closely spaced T's. So all the manufacturers kind of throw it out there. They don't say why, but they say do it. So why? So who invented it? Well, like everything else we've talked about, this guy keeps coming back. Gil Carlson years ago developed this pumping concept, primary, secondary. And like everything, necessity is the mother of invention. So they have a large problem job down in New York City years ago. And he's a young engineer, and he gets asked by Bell and Gossett, fly out to New York, go help the B&G the B&G factory office in New York City. They got this problem. So monoflow systems, which I'm sure you probably never even heard of today. But years ago, that was a really very common design principle on how to install hydronic systems in these large buildings. And so what happened was they had 10 garden-style buildings. So big project. And they had this massive boiler plant, central plant, that fed these 10 buildings. And the problem was when they turned the system on, when they were going to commission it right at the end of the summer, getting ready for the heating season, they had the boiler plant running fine. They had hot water flowing through the mains. They had hot water flowing into the buildings, and they had no heat at all of the convectors, all of the terminal units in all of the garden-style buildings, garden-style apartment buildings. And what had happened was they had 2 engineering firms that were designing the system because the project was so big. So they had one engineering firm that was responsible for the building, piping, and radiation. So once they got inside each of these 10 buildings, they did the piping and the radiation. And they oversized the piping by mistake. And the result was, because the piping was so oversized, they couldn't create enough pressure drop to cause flow to go through these monoflow fittings. I'll show you real quickly in a second what I mean. The second engineering firm, they were responsible for the boiler plant and then the main distribution. And they made the mistake of undersizing the main. So they have one engineering firm that's providing heat, but the piping is technically a little bit undersized. And then you have a second engineering firm that was responsible for the plumbing, the piping in each building and the radiation, and they were actually oversized. And it was like a perfect storm. And the mistake on both of these created the scenario where when they turned the pumps on and they had flow throughout the 10 buildings, and they would flow individually into the buildings, They couldn't get heat out of the radiation. So this is just a real quick cartoon drawing of a monoflow system. So you have a standard T, and then you have this cone, this reduced opening, and it's an engineered pressure drop at the end of the day. It's an engineered pressure drop. And the way it would work is the water moving along the main here, the velocity along the main created pressure drop because of that cone. You're trying to shove all this flow through a reduced hole. And because of that, some of the water would say, you know what? It's a hell of a lot easier for me to get off the standard T, and I'll go up and I'll go through the radiation. So I have a small portion of me leave the main, go through the radiation, come back down on the other side of that cone, and I'd rejoin. So it was an engineered pressure drop using one pump, and it would feed all these terminal units. Well, they oversized this piping, that one engineering firm, and then the other engineering firm on the main undersized it. So the flow getting into each building was a little too low. And then the piping it was going in was too big. So the point was the velocity along here was too slow. So it didn't create the pressure drop here. So it didn't cause the flow through the radiation. They get 10 buildings. I mean, the big problem. So they at the time, years ago, there were no reps, there were factories. So the New York factory guys are out there and they're looking at it and they're like, what are we going to, they call the factory. They say, hey, Gil, hop on a plane, fly out of Chicago, go to New York, see what you can figure out. So he goes out there. And this is kind of again, kind of a weird drawing, but that's what he's dealing with. And what he determined after spending a little bit of time there is that the flow in the distribution main was about half of what it should be. So flow into the buildings was half of what it should be. The building radiation was designed for 200-degree water to enter into these radiators. I'm only showing 4. There was hundreds and hundreds of them. And it was designed on a 20-degree. There's that famous, we talked about it earlier, that 20-degree delta T, that temperature drop. So if it's coming into the building at 200, it should be returning at about 180 from each building. So the radiation was all selected, already installed based on this number, 200 to 180. So what he does after doing some calculations and he's looking at the problem, he says, I want you as a contractor and through the factory office, I want you to install these booster pumps in every building. And the booster pumps are going to be sized for each individual building. And so the factory people are saying, well, wait a minute, Gil, I've got this big, 50, 75 horsepower central distribution pump that's supposed to be feeding all of these buildings. And I don't want to put these smaller booster pumps in series because this big ass pump is just going to ruin, it's going to overturn, it's going to rip couplers, it's going to overload the motors on these smaller. We don't want to do that. Of course, he knows this, but he's explaining what he wants them to do. And he said, after you put these booster pumps in, I want you to do this. I want you to put a piece of pipe between the supply and the return of each building. Now, so up until this point, that never happened, never existed. No one even knew like to think about this. And he could see it. And he said, what I want to do is I want to decouple these smaller little pumps that I'm going to size for that particular building's needs, his flow and load. And I still have my distribution, but I'll decouple it. So this guy is not kicking the daylights out of these smaller guys. So it's a simple little thing, but it's not, but it is. And that's what he did. He had them do it. And they're like, well, we're up against it. We've tried everything we can't fit. Okay, we'll do it. And they do. And this is the term he used. I want to hydraulically isolate the pumps from each other. It's like, and again, hydronics was kind of in its infancy as this was happening. So no one had done anything like this. And so he did. And they turn on the pumps. They turn the boiler temperature up a little higher. I'll explain that later. But they increased the 200-degree water that they talked about to a higher number. And as this pump's pumping along, a certain amount of flow was going to be directed into this building. This pump was he was sized for this building's load. Now all of a sudden this pump could give the appropriate flow rate, the velocity to get the pressure drop at that monoflow so flow would go through. All 10 buildings work. They put in these common pipes. They put in these smaller booster pumps for the buildings. He hops on a plane, goes back to the factory, doesn't say a word to anybody. The factory guys in New York City are like, I don't know what he just did. I don't know what happened, but we solved the problem and the building's working perfectly fine. And the owner of the place is completely happy. So the engineers, which at the time he was kind of a young guy, he goes back and the lead engineers at B&G are like, come into the conference room. Will you tell us what you did? And he goes, well, I figured out that they undersized the flow here and the piping was a little too big there, so they weren't getting the pressure drop. So I told them to put booster pumps. You can't put booster pumps in there. They'll be in series. He goes, oh no, I know. I had them put a decoupler, a piece of pipe between this. And the lead engineers at B&G are like, what? They never could see it. Never, what are you talking about? And he explained. And so he sat and talked to them, and to the point where, and you guys have a copy of this in that binder that you got the first week, but it went from like didn't exist to like a manual on primary, secondary that he developed. And so he starts talking about, he says, look at a real basic statement. And he was very, very smart, very dry. And you read it, you fall asleep. When two piping circuits are interconnected, flow in one will cause flow in the other to a degree, depending upon the pressure drop in the piping common to both. I mean, talk about wordy at the end of the day. Flow in one circuit will cause flow in the other circuit based upon the pressure drop in the piping common to both. And that's why it wasn't working. This flow was too low because the engineers that designed the distribution undersized the piping. The engineers that designed the building piping, a little too big. So flow in one will cause flow in the other based on the pressure drop that didn't exist. So he kind of worked it backwards. And he said, a fundamental rule for primary secondary design is when two piping circuits are interconnected, flow in one will not cause flow in the other if the pressure drop in the piping common to both is eliminated. And the way you eliminate it is he would take that monoflow T, get rid of it, take two standard T's and get them close together. And then flow in one will not cause flow in the other if the pressure drop in the piping common to both is eliminated. You put a gauge right here at point A and a gauge at point B. Is there a difference? Absolutely. Is it insignificant? Absolutely. So you got this pump flowing along and it will not go through that secondary circuit. And then what would happen is you'd have a secondary pump so those were the booster pumps that he added to the 10 buildings. And that was the beginning of primary, secondary that you guys design, your firms design. It's used all the time with chillers, boilers, radiant heat, and all of that. It was a problem job that he solved and he could see. Chillers, another, the chiller manufacturers might reference, going the wrong way, a decoupling pipe. You got your chiller pumps, you got your distribution, they coexist, they're not fighting each other. So this is all different examples. So in that manual, and he talked about this when he went around to ASHRAE around the country, talking about this concept. He would use this thing. He called it the law of the T, which sounds kind of silly, but what it'd say is the flow rate in gallons a minute entering a T must equal the flow rate leaving that T. And that's kind of the principle of what's going on here. Water entering that T, whatever that flow rate is, at some point has to equal the flow rate leaving that T. So then he starts building, okay, they got three scenarios. The first scenario would be if this primary flow rate was equal to the secondary flow rate. So I got a pump here and I got a pump here. And these look like they're spread out, but he's saying, hey, this is my decoupler, this is my common pipe. And when the flow is equal, 70 gallons a minute flowing along the primary, if that secondary pump turns on and he's pumping that same flow rate, I got 70 gallons a minute going through that secondary circuit. And I would have 0 gallons a minute in the main, in this common pipe. If I turn this pump on, oh, excuse me, if I turn this pump off, what would I have for flow in the common pipe? 70. Turn it back on, equal 70. 70 gallons a minute enters the T. In this case, this pump is pumping the same flow rate. So he's taking this 70, enters this back to 70. So that's one scenario. No flow in the common. Secondary supply has to be equal to the primary supply because they're the same flow rate. And the primary return temp is going to be equal to the secondary because, again, same flow rate. No flow across the common. Second scenario, primary flow is less than. So this GPM here is going to be lower than this. So in this case here, we have 40 gallons a minute on the primary, and we have 55 gallons a minute on the secondary. You say, well, how can that happen? And again, this decoupling, but what he'll say is that 55 gallons a minute coming back here, it hits this T, which way do I go? And 40 is going to go this way to match this 40. And then 15 is going to go backwards. So when I blend the 40 and the 15, there's my 55. That's another scenario. Primary is less than secondary. So then you get into this thing here, a mixing T and a diverting T. So I'm taking 15 from the return and I'm mixing it with 40 from the hot, call it hot, whatever, it's chilled water or hot water, but I'm mixing, so I have a mixed supply going to this 55. And then from a diverting, what happens is mixing is 2 ins, 1 out. So mixing T, 1, 2 ins, 1 out. Diverting is 1 in, 2 outs. So I'm not mixing at the diverting T, I'm diverting. So in this case, 55 comes down, 15 goes back, 40 goes. So reverse flow in the common is one of the characteristics when the primary is less than the secondary. Secondary supply can't match the primary. Why? Why can't this flow rate be, this temperature here be the same as this? Different flows, but means, what am I doing? Yeah, I'm taking return water and I'm cooling down the hot. So it can't be the same. That might be by design. Maybe I'm mixing it down intentionally as you start getting into like thinking about systems. But the primary return will equal because I'm taking some of that return water. I'm going this way. So whatever comes back here, that is my temperature there. There's no mixing. The only mixing is right back here. So that's like second scenario, if you will, primary less than. And then the third example he will talk about is primary flow is greater than the secondary. So throw some numbers, 45 and 30. So I got 45 gallons a minute entering this T. I have this pump up here that wants to pump 30. So what happens? As I enter the T at 45, 30 goes this way. 15 is now going to go across the common in a forward motion. So am I changing the temperature going to the secondary zone here? I can't because I'm pumping that flow rate and I'm taking 30 of it moving through the zone. So I haven't done any mixing. What have I done with it? Where's the mixing now? Then that becomes my diverting T, and this becomes my mixing T. So now I'm taking some hot boiler water. Some of it goes up through the load. Some of it stays across the common. Now I take this return cooler water and I mix. This is a very, very primitive where you might get into, and we would get into it over the years. I want boiler return protection. I get cold water coming back from a building. Well, I might take some hot boiler water, put it down the return and blend, mix. And I can do that intentionally. So it's just a quick example, but you have the flows are equal, the primary is greater, the primary is less. Forward flow in the common pipe, that's what he's calling it, forward flow. Secondary supply equals the primary, right? So whatever that temperature is here, that's the temperature going there. Just less flow of it. Lower flow, less flow. I can't even speak English, but it's the same temp. But the return temperature can't be the same. This return is now being blended with some of this hot water across the common for a blended mixed 45. Yep. No, meaning like, I mean, today, like today. uh, Yep. Yep. Yeah. It was a way of not having like extra pumps. You could use this one pump. They would have these manuals from years ago. This is in the 40s, in the 50s. And they would have monoflow systems, how to design buildings, 10-story building or a one-story residential home with monoflow fittings. So the fittings would have been just in the on the terminal units themselves. So once you get into the building, it was that main that would have like a supply T and a monoflow T. That's your pressure drop. So as the water's going, pressure drop here, some of it diverts through that radiator back onto the main, but not going from building to building. There would be that would just be in the inside the each individual building they would be using, but it would just be a two pipe system feeding and then a return coming back on the return. Yes, correct. Yep. Yes, sir. Yeah, yes. So before they had the problems, when it was designed right, it worked. It worked. It was and we look back at it today, so that's so primitive and limited control and blah blah blah. But it was all at the beginning, it was going from not having it. How can I get all of this in? Yep. Okay. Oh yeah, temperature degradation. It's dropping. Increase the radiation size of the terminal unit. Correct. 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 It doesn't make sense. Correct. Correct. But it was just at the beginning, so they were just glad, but then realizing, so as you like invent something, you find out all the good and then you find the bad. Now you got to come up with something. The main return. Yeah. Very complex. Correct. Right. Right. So anyways, I don't want to go through a heat balance equation with you tonight, but all is referring to just from a visual. And this was an example he would talk about in the book. He's saying, hey, I got a load up here. This load could be a building. So I got this main coming from a boiler plant. I got 210-degree water available coming from the boiler plant, and I'm going to have this, whatever it is, but it's a 200,000 BTU load. And I'm going to design it on an average mean water temp of 140 with a 20-degree delta T. So if it's 20 degrees, right, 10 and 10. So if that's my mean, I got 150 on one side, 130 on the other. There's my 20 degrees. There's my 20 gallons a minute, right? 20-degree delta T, 200,000 BTUs. So I've got this 20-gallon a minute pump doing this. That's how I've sized my terminal unit for this 150 to 130. And I have available 210. So he says, okay, figure it out. How do you calculate this? I got 210-degree water here. Well, this is going to be 20 gallons a minute. So I got to figure out, I got this pump back here that I can't see in this drawing that's feeding all of these crossovers. And this is one of them. So I've got like a balance valve so I can balance it. And I make sure I have the right flow rate coming across here. But the point is the expression he would refer to is he'd call it a heat balance equation. So he's saying, okay, we talk about that system size and we talk about BTUs and GPM and delta T. So he's saying, okay, if I have 210-degree water right here, right? And if I design this properly, I'm going to have 130-degree water right there. How am I going to get that 200 down to 150? I got to return water back with the 210 to get to 150, right? So then he's saying, okay, well, if I got 210 here and I got 130 there, what's the load up here? 200,000 BTUs. So this job of this crossover bridge right here is to deliver 200,000 BTUs. This is the load up here that he's trying to deliver, 200,000 BTUs that's designed at a 20-degree delta T, 150 to 130. So what's the delta T on this loop right here? 80. 210 to 130. So I'll take your system size and say, hey, 200,000 BTUs and 80-degree delta T. That's all it is. Like when you look at the wheel, you're like, you would never design a system to have an 80-degree delta T. No, you wouldn't. Like radiation going to a house or apartment or a school. But on a crossover primary secondary, if I have a boiler plant that's running at that temperature, maybe I do. So now all of a sudden he does the math and he says, hey, assume a crossover bridge supply of 210 and a return temp. I got an 80-degree delta T. Do the math. I need 5 gallons a minute. That's it. So I need 5 gallons a minute of 210 moving across here. Now, when that pump turns on and he's pumping his 20 gallons a minute, he's going to say, hey, 20 coming here, 15 is going to go backwards of that 130 to blend with the 5 at 210. And when you do the math, it's a 20 gallons a minute at 150-degree water. That's primary, secondary, right there. Multiple boilers, multiple chillers, blah, whatever you got. Right here. No, that's a pump. Well, this right here, this is the primary. We'll call it whatever you call it, primary, secondary. This is a two-pipe system, a supply and a return, and he's got a crossover is what he would. Yeah, that'd be balanced based on right here that you can't see. I've got this big distribution pump that's feeding, say, a bunch of bridges, a bunch of crossovers. But he doesn't care about the flow and the terminal unit pressure drop up here. That's going to be taken care of by this guy here. I need to provide the design flow for all of these. If I had a bunch of them. And there'll be other pictures that make a little more sense, but yeah, this guy here, yeah. So if I'm like a pump, high pressure, low pressure, the high wants to get to low, I want to cut across this bridge and get right back to the section of that pump. So I'm going to use that balancing device to throttle down and make sure I have, in theory, 5 gallons a minute. That's what I'm chasing. Yes, sir.
I'm sorry. In reality, no, no.
Well, you could use, but that three-way valve would be here, one of these two. Well, but if it's up here, then it's never going to see that pressure drop. Unless you connect it. I know where you're going. They would use that three-way valve, the CV of the three-way valve, as pressure drop for balancing to get that 5 gallons a minute across.
And
Heat balance. All he's saying here is 15 times 130 plus 5 times 210. 15 times 130 plus 5 times 210 is equal to 20 at 150. That's it. Yes, sir. So what that's showing is 200,000 BTUs divided by 8.33 pounds times 60 minutes. That's the 500 times your delta T, which normally would say at the beginning when you're talking would say heating, so always a 20-degree delta T. But because we're got this kind of weird scenario here of a high temperature differential, the delta T is not 20, it's 80. So I can use 5 gallons a minute and move 200,000 BTUs as long as I allow a 80-degree delta T.
Yeah.
3 times 60 minutes in an hour. Yeah. Yes. Yes. 500 or 499.8, whatever. So this is just a quick example of what they would refer to this as a one pipe primary secondary. And to your point earlier, if I have this scenario, right, what happens as I take heat up through this load? The temperature that was at that T can't be the temperature at this T, correct? I have temperature degradation. So the supply temperature here for this load is going to be different than the supply temperature for this T, for this load, right? So one pipe, I got to account for that. So just it's more about information. Two pipe, now the temperature at this T could be the same as this T, and the same as this T, and the same as this T. So I'm not affecting my temperature degradation. It's a little more complex than a single one pipe main with a bunch of closely spaced, call it, but a much better control and not affecting whatever's happening in the individual buildings doesn't affect downstream performance or output. So again, you can get into all kinds of scenarios, and that's what they would do. You get into VFD drives on the pumps we talked about earlier, the eco circs that have the drives right on board the pumps, and they might have a valve, control valves either on, off, or modulating, and these pumps can respond to the pressure differential from energy savings. You've got, in this case here, maybe hot water moving across, depending upon the load. This control valve could be, you can go around that rabbit hole real quick. But at the end of the day, it's just all about, I've got a distribution pump that's providing flow across this, and he's not affecting secondary pumps or tertiary pumps or whatever the terminology we want to use. And again, multiple chillers. The chiller manufacturers have been, kind of embraced the piping as a concept for a long time. This would be actually, I think it was out of a train manual, and it was just, they refer to it as a classic primary secondary, but decoupled was the term. Yeah, train. I was going to say, I think it was out of a train manual, Yeah, exactly. And so chiller pumps dedicated to each chiller, and then maybe going out to fan coils, very simple drawing, but maybe a VFD drive variable speed pump going out to my chilled water coils, hundreds of them perhaps, in a complex. And then they just had different, variations, and they'd have control valves. So then either pump could go through the particular chiller. They started getting into some pretty fancy sequence of operation and how they bring chillers on and off and etc. Same thing, whether it be chillers. Now we're in a boiler plant. Got multiple boilers. These could be, 4 million. I got 16 million BTUs here, each with its own boiler pump on a manifold feeding a massive complex, or maybe it could be like the boiler plant that's feeding a campus. It could be college dorms, college office buildings. It could be a hospital. It could be anything. But distribution pumping, now again, simple little pump right here, but you're probably talking, 50, 100 horsepower base mounted pumps, 2 or 3 of them. And then I got these boiler pumps supporting the 400 gallons a minute if I'm doing a 20-degree delta T, so 1,600 gallons. A lot going on here. But what's interesting is right there, those scenarios that I talked about, as only one boiler is running and the other 3 are off, right? And he's introducing and this guy here is pumping the building or the buildings, you're going to get some blending. You're going to get some mixing by design. And that's okay. And you get some kind of supply sensor feeding back to the BMS system that's controlling the fire in these boilers saying, hey, I need more, I need less, bring on a boiler, increase the firing rate, bring on two. All of that's happening all the time. And the one scenario that could happen that you don't want to have happen is when, in this case here for heating, is when the flow here is greater than the flow here. Because now if I'm over pumping here, some of my hot water is going to go what? It's going to go backwards and it's going to elevate my return temperature. And the problem with that would just be if I've got this high efficiency condensing plant and I'm elevating my inlet temperature, I'm reducing my efficiency. So there want to be some intelligence, back here to try to prevent that from happening. Maybe variable speed pumps on the boilers, and they'd start to ramp down. Yeah, a lot of times the control logic on the new boilers. Yeah, right, correct. We don't have to get into this. We already talked about loss headers, but the point being from a primary secondary conversation is this could be used for primary secondary. And they just throw some scenarios. They say the flow rate's the same. The flow rate's greater on one side, the flow rate's greater on the boiler side. You can get mixing going on. But what I want to get to just real quickly, when you have this variable, now I got a variable primary, and maybe the engineering office and the engineering firm says, I don't want all these extra pumps. I want this one pump that's going to provide flow through my source, maybe chiller, and then it's also going to provide flow through my either different buildings or different loads within the building. And I can have some feedback. I have a pressure differential sensor for variable speed going out, as these valves start to close down, I can start to ramp down. And then I have minimum flow probably across the chiller. So I have this. So I got to honor that as well. So there's a lot going on there. System pumps are variable and they push water through both the source and the load. The variable primary chilled water pumps maintain differential pressure in the system. Minimum flow valves maintain chiller minimum flow by controlling the differential pressure across the chiller. So there's ways of getting there. It's God bless you. There's a little bit of and so this is not primary secondary. There is no primary secondary. It's variable primary flowing through both the chiller plant and the chiller plant and the distribution. So there are some options, I don't know. Some firms, believe in it. Others they just stay with the primary secondary. Yes. Chiller barrel or whatever. They don't want to reduce it too low. Yep. You're not taking that refrigerant, that cooling away, and it'll freeze. So there's minimum flow. So sometimes if you dedicate pumps to the chiller, you take away that concern because you have the adequate, appropriate flow. These are just some quick examples, but what I want to really get to is this last example here. Integrate multiple energy sources with primary, secondary. So we're showing a scenario here where we have some air source heat pumps being specified and installed in a building. We have some heat recovery chillers, and then we have a more traditional, call it a gas-fired condensing 20 million BTU boiler plant. The boilers have their own pumps. The air source heat pumps have their own pump. The heat recovery chillers have their own pumps. And so what they're trying to do here is, with a lot of pressure coming from the industry about electrification and decarbonization and reducing the amount of carbon that perhaps I'm using on this site, can I run electricity? Can I just use the air source chillers? Can I use the heat recovery chillers for providing heat? And so we kind of go through some scenarios and we say, hey, look at when the outdoor temperature maybe is greater than 30 degrees and the load, whatever the load is, maybe my air source heat pump and maybe even part of my heat recovery chillers can provide some capacity and I won't rely on my boiler plant. So we'll kind of go through some scenarios saying, hey, I got 1,000 gallons a minute at 120 going out to the building, which means, and again, back to that 20 degree, you got 100-degree water coming back at a flow rate of 1,000. And I got a heat recovery chiller. What did I say back here? I got 5 million BTUs here and I got 5 million BTUs there. So 500 gallons a minute of 100-degree water coming back. 500 goes across because there's my flow, 1,000 gallons a minute, hit the T. 500 goes this way. 500 goes across the common. I have 500 of 120-degree water coming from my heat recovery chillers that I want to grab. So then I get some blending taking place, right? So now I have 1,000 at 110, and I'm chasing a supply temp of 120. And then my next source of energy could be this air source heat pump. And I have 1,000 gallons a minute of 110 moving back this way, no flow across the common, right? Because I'm back to 1,000, so I got 1,000 here. I have a 10-degree rise across the air source heat pump, not 20, but a 10-degree, which is probably more common. So now I have 1,000 gallons a minute of 120, no flow across the common. And that's going to now go across that 1,000 gallons at 120, going across that decoupler out to my building. So I could have a scenario where I am relying on all electric to provide 120-degree water at 1,000 gallons a minute out to the building. And boiler plant, correct. Exactly. And then they say, hey, it's less than 30 degrees outside. So the load may be starting to get a little greater on the building. What could happen? Maybe I'm up to a 1,500 gallons a minute at 120. Coming back at 100, there's that 20 degrees coming back. So then again, I'll have the same scenario, say, hey, 500, grab, what can I grab? I can pick up 20 degrees here, but at a flow rate of 500. So a portion of that stays across the common. In this case, it's 1,000 gallons a minute because I've increased the flow rate on my variable speed distribution because of the load. So I get 1,000 at 100 across the common, 500 at 100 comes back at 500 at 120. I got a blended 1,500 at 107. So I'm still not there, but I've picked up some energy. Now I encounter my air source heat pump, 1,000 gallons a minute at 107, 10-degree rise, right? 500 goes across the common at 107, but 1,000 at 117 comes back from my air source. So when I do the math, and again, it's just math, I got 1,500 at 113. I'm chasing 120. So maybe now I need some help from the boiler plant, but I don't need the whole boiler plant. I just need enough energy to take my 113 and bump it up. So I'm providing 120. So now maybe I have 1,000 gallons a minute going across the decoupler, and I have 500 gallons a minute going to this first. I got 20 million BTUs. I have 5 million BTU boilers. So 500 at 113, coming out at 133, 20-degree temperature rise. Off of this one boiler, the other three are off, so there's no flow through them. I have 500 gallons at 133, meeting 1,000 at what, 113 right here. And I'd be back to 1,500 at 120. You do that heat balance equation, that little simple example I did before. So that happens. That goes across all the time. And so I can have all of this different pumping. These pumps don't even know the other exists, and they're all working together without fighting each other. All because of the decoupling, the low pressure drop, whatever term you want to use, so they're not in series and fighting each other. And then the final scenario would be, hey, It is cold. It's New England. It's Boston. It got real cold. Maybe the COPs and this heat, the air source, there's nothing there. Potentially nothing. So I'm, whatever the load, 2,000 gallons a minute at 120, coming back at 2,100, goes across, no flow from my chiller, no flow from my air source. And now I'm going to my boiler plant, more traditional, nothing across the decoupler, 2,000, 500 here, 500 there, 500, 500, picking up my energy, coming back at a 2,000 at, 120. So now I have to use my gas on that really cold day. So and this is what you guys as engineering firms are being challenged with clients that are trying to chase after this electrification, reduce our carbon footprint, decarb. But in the end of the day, I can't get rid of the legacy. I got to hold on to it when I need it. But, so then how do I build a scenario and have a sequence of operation where I can grab the energy when it's there? And then when it's really not, because it's really cold, okay, now I have my boiler plant for my more traditional. Primary, secondary in an hour. Hold on. Yeah, yeah, sequence, right? Building management that's bringing on, correct. But it's all based on, because it's saying, hey, air source, I'm at 0. I probably can't grab enough energy out of the air source heat pump, right? So I could do it. I could spin the electric meter and pick up a couple of degrees. What a waste of energy. What's the cost of a therm of natural gas versus a kW of? So that's when they start to balance and saying, hey, I know you think gas is bad, but right now gas is really good when it's 0 out. When it's 30, okay, we'll shut him off and we can use the electric, and the COP's high enough on my heat pumps that it might make sense. If I got a COP of 2.5 or 3.0, okay, for 1 kW, I'm getting 3 kW worth. Okay, that makes sense. I can justify that. So I'm looking at system conditions. Say it again. Uh, how cold is it outside? It might be as high as 3.5. Well, yeah, it's the fact that we're having this conversation in and of itself is kind of crazy, but it is. It's being legislated. I mean, have you guys ever heard the expression BERDO? BERD? Okay, see, you're all shaking here or no? So they're getting, oh, Will would have talked about it. Would have talked about it. So they're fining building owners if they don't do stuff like this.
You was a copy-paste life form too.
Malthusian.
I was wondering if we have time to bring it up.
Same. Different terms. It's evolved. Like when you sit down at night and you're bored to death and you start to read this, you're not going to see the word decoupler. As it evolved, chiller manufacturers say, hey, there's a value that we can use and benefit our chiller operation. Boiler manufacturers kind of jumped in. And so all of a sudden, and then just engineers, they're all looking at it and they all have their own opinion. So, primary, secondary, tertiary, decoupler, closely common, it's all the same. It's just understanding that, like when you're dealing with large diameter pipe, like we were talking about here, it's not 12 inches. Could be 10 feet, but relative to, yeah, yeah, right. So that's okay. It's just that if the scenario, what he's trying to harp in the original design manual was, if you take those T's and you start to do this, spread them apart, what happens to the pressure drop between the two? It starts to go up. Then you start to lose control. So really minimize that pressure drop. Well, now you start applying that they weren't even thinking about 50 years ago, 60 years ago. So, they realize they're saying, look, between this point and this point, if it's like 1 foot, 1.5 feet of pressure drop, it's fine. Yeah, because you're dealing with 50, 60, 100 feet of pressure drop on your it's fine. It's just more about minimize so that the pumps aren't, like, you just don't want pumps with different capacities in series fighting each other. So, yeah, that monoflow building, yep. Design, yes. Probably. There's probably a bunch of different scenarios that, but it's all plumbed, it's all piped, it's ready to go. It's following the engineering drawings. Here we go. Or we're gonna repipe the whole 10 buildings. There could be a bunch of answers. They were trying to get out of it without doing anything because they, because it's done. The contractor bid the job, right? And so he gets awarded. So he can only bid it for this. This engineering firm got hired for that, this guy, and and they turn them on and they have no heat in the buildings. But the boiler plant's hot as hell. The mains are hot as hell. They just can't get it into the. So he just, what was an example of it was just this guy kind of lived on a different planet in a positive way. Like he could see things in his mind. Yeah. And that was the beauty of him is he could take some really complex things and really make it simple. So you can understand and apply it and use it. So anyways, listen, we are done 4 weeks. Thank you guys very, very much. Both remote and here in person. We really appreciate the time. Just want to see what we got going on here. 3 participants. So Carla and Liam are still on. I just want to say thank you guys. And we're about to shut down the Zoom presentation. So anyone that was supposed to be here and didn't make it, will get things mailed out to you, certificates, etc. So thank you all for spending your time remotely with us.
Thank you.
Thank
Okay.
you. Have a good night.
You guys too. Thank you again. Bye-bye now.
Bye.